in a uniform magnetic field. First we consider that the particle is entering a uniform magnetic field region in perpendicular direction. That means if the charged particle is moving normal to the magnetic field. Let us consider a uniform magnetic field B acting perpendicularly into the board and a charged particle of charge q and mass m enter the region of the magnetic field with velocity v and perpendicular to the magnetic field. That is, direction of v is perpendicular to the magnetic field. Clear? Now let us see. We have already considered that this is the magnetic field into the ball and charge particle of charge q mass m enters the region in this direction. This particular, see here, right? This is the magnetic field direction into the ball, and this is the direction of the charge particle, moving charge particle. Let us write this. Here a charge particle moving this enter this region and it is moving in this direction. This is the direction of B, which is into the ball. Then force on the charge particle Q is force on the charge particle is Q into V cross B, which is equals to QVB sin 90 degree. QVB sin 90 degree. Therefore, F is equal to QVB. And what will be its direction? See here. This is the direction of the what? Magnetic field, and this is the direction of V. Now, just put in this direction into the board, and this is the direction of velocity. Then V cross B, you rotate a right-handed screw from V to B, it will be in the anti-clockwise direction and direction will be along this direction. Therefore, the force on the charge particle will be along this direction, and this is perpendicular to V. This is perpendicular to V as well as B. Right? This is the direction of force. Right? And this force is always perpendicular to the direction of the motion as well as the direction of the magnetic field. Thus, the path of the charge particle will be circular. At each and every point, say here, the direction of velocity is along this direction, force will be along this direction. At this point, velocity is along this direction, force will be along this direction. At this point, velocity is along this direction, force will be along this direction. That means it will rotate. This will be the trajectory of the charged particle. Since the direction of force is always perpendicular to the direction of velocity, then the particle will rotate. That means its path will be circular, right? And since F is perpendicular to V, therefore no work is done to the charged particle. So the magnitude of velocity remains the same. Magnitude of velocity remains the same. If a particle of mass m moving in a circular path of radius r with uniform speed v, then the necessary centripetal force is mv square by r. If a particle of mass m is moving in a circle of radius r with uniform speed v, then that particle needs a centripetal force equals to mv square by r. And in this case, the centripetal force is provided by the magnetic force on the particle, which is qvb. Therefore, from here you can write r is equal to mv square by qvb, which is mv by qb. This is the radius of the circular path. This is the radius of the circular path, right? Now see here, radius of the circular path is directly proportional to the momentum of the charged particle. Momentum of the charged particle. The larger the momentum, the larger will be the radius, and bigger the circle described. If omega is the angular frequency, then omega is equal to, we know that omega is equal to v by r. So we can write v divided by r is mv by qv, or you may write qv by m. And see here, angular frequency is independent of velocity. Angular frequency is independent of velocity, that means independent of energy. And this frequency is called gyro frequency. Omega is called the gyro frequency, right? And if nu is the frequency, of rotation, then nu is equal to omega by 2 pi. That means qb by 2 pi m, which is also independent of velocity and so the energy of the charged particle. This is called the cyclotron frequency. Cyclotron frequency. Nu is this, and therefore the time period. What will be the time period? Time period is the time required to complete one revolution, which is 1 by u, and that is 2 pi m by qb. 2 pi m by qb is the time period of the charged particle, and it is also independent of the speed of the particle and also radius of the path, radius of the circular path. It is independent of radius of the circular path. Whatever the radius, the time period is same. It is only depend on the mass, charge and intensity of the magnetic field. And this result or this concept is used in a device called the cyclotron, in which we can produce high energy charged particles. We will discuss later on. Now, if the charged particle enters a region with magnetic field V in parallel or anti-parallel, that means a moving charged particle does not experience any force if its motion is parallel or anti-parallel to the magnetic force. That is, if V is parallel to B or anti-parallel to B. Case 2, if V is parallel to B or anti-parallel to B, then force experienced by the charged particle is 0. Right? That means it will travel with uniform velocity. Case 3. If the charged particle enters the region of the magnetic field with an angle, we have taken this as perpendicular. If it is not perpendicular and also not parallel and anti-parallel, that is, the direction of V makes an angle theta with B, then what happens? Then that V, that is velocity, can be divided into two components. One is along the magnetic field perpendicular to the magnetic field. This is x direction, this is y direction. Let us consider a charged particle q and mass m moving with velocity v at an angle theta with the magnetic field. Let us say magnetic field is along the x direction and particle is entering the region with velocity v making an angle theta with the magnetic field. Then this v has two components. One is along x direction, which is Vx is equal to v cos theta, and which is also along the direction of magnetic field. And another is perpendicular to the magnetic field, which is Vy is equal to v sin theta. Since a charged particle moving parallel or antiparallel to the magnetic field does not experience any force, so due to this component, the charged particle does not experience any force. Therefore, it will move along the direction of magnetic field with velocity this. But due to this component, it will experience a force, and that force is equal to, already we have written qvb. Now here q v sin theta into v, because in this case velocity is v sin theta. V sin theta is the amount of velocity which is perpendicular to the magnetic field, and due to that velocity it will experience a force which is perpendicular to the v sin theta component as well as b direction of b, and that is that force is this, and due to this force it will rotate or it will move in a circular path. Already we have discussed, right? And the radius of the circular path r, then r will be equal to, already we have written that, what? R is mv by qv. That was the expression, mv by qv. Now here you have to written mv sin theta divided by q into v, because v should be replaced by v sin theta. Here v is v sin theta, and therefore the time period of the particle t is 2 pi r by v sin theta. V sin theta is the velocity. Now 2 pi into r is mv sin theta divided by qv divided by v sin theta. Again you get 2 pi m by qv. 2 pi m by qv is the time period. That means the time elapsed in one revolution is t. Therefore, the charged particle is under the combined effect of two components of velocity. It moves along the direction of the magnetic field due to the v cos theta component, that is horizontal component, and at the same time it will move or it moves in a circular path due to the v sin theta component, that is normal component of the velocity. Thus the resultant path of the particle is a helix. That means it will move along the direction of the magnetic field as well as it will rotate. That means this will, like this, will be the path of the charged particle. Thus the resultant path of the particle will be helix, right? Whose radius is this and time period will be given by this, and axis of the helix is parallel to the direction of b, and the linear distance traveled by the charged particle in one rotation is called the pitch of the helix. Therefore pitch of the helix, p, which is called pitch of the helix. Is P is equal to what? It is the linear distance, that is distance travels in x direction, which is the velocity along the direction of the magnetic field multiplied by the time period, and this will be equal to v cos theta into t is 2 pi m by qb. That means you get 2 pi m v cos theta by qb is the pitch of the helical path.